This is going to be a quick follow-up lecture to the idea of particle models, and we're going to use them to help justify the shape of atomic orbitals. So you've probably seen atomic orbitals for most of your chemistry career so far, and maybe you've just taken the shape for granted so far. This is going to go a little bit towards explaining why the orbitals are that shaped. And we can do that from the particle models we've previously covered. So we'll recap those very briefly, and then how do they end up relating to atomic orbitals? So the first two models we came across were the particles that were sat into a box. So these are very basic model systems. They involve particles that cannot escape their box, and there's no potential energy in there. They're not incredibly realistic, but they are good starting points because the 1D box gives us quantized energy. Quantized energy, really good. That's exactly what we see in the real world. It's why things are coloured. It's why spectra look the way they do. If we didn't have quantization of energy, most of chemistry wouldn't really work as it does. And we can also work out from that energy is really proportional to a quantum number squared. So while we can govern the wave function by a quantum number, the energy will be n squared. That pops up a little bit in various forms of physics. The spectroscopy of the Rydberg equation, for instance, all the quantum numbers are squared in that. So it's nice to see that in a model system as well. When we get to the 2D box, we get degeneracy. That means that we can have more than one quantum state or more than one wave function that has the same energy. It basically means we get a choice of how we want to distribute the energy. Do we want to distribute it in the x direction or the y direction? And if the x and y direction are identical, if they're the same size, if it's a perfect square box, well, we get two possible states with identical energies. The energy there is proportional to n squared plus n squared for the two different directions, and you can easily expand that into a three-dimensional box. As we go through into atomic orbitals, especially atomic orbitals in 3 dimensions, it actually goes up above threefold degeneracy. It's a little bit more complicated than that because it's less about 3 physical directions of up, across, and forward and back, and about degrees of freedom. And when we have degrees of freedom of, say, quantum numbers, we can distribute energy around. So we added 2 more model systems, a particle on a ring. Here we confined it to a one-dimensional ring. It's exactly the same as a 1D box, except it loops around the start as the same as the finish. Or, as we might call it, a periodic boundary condition. The function that governs it must be periodic. Now there, we also had 2 energy levels. We also had degeneracy, except when the quantum number was equal to 0, in which case we only had the 1. And that's all related to angular momentum. And one interpretation of that is that when the quantum number is 0, there is no angular momentum. There is no orbiting motion on the particle in a ring. It's effectively everywhere at once. It doesn't have a build-up of probability anywhere around the ring. And then we tried the potential well. This, also known as the quantum harmonic oscillator, that's the fundamental building block of most vibrational spectroscopy. That told us that the wave function tended to 0 at infinite distance. There is no maximum distance that the particle could be from the minimum point on the potential well. It could go anywhere. And that we also see in real wave functions. They only tend to 0 at infinite distance. So that means the wave functions governing any atoms in your body right now do reach out across the entire universe. They don't end. They are interacting with everything, which is quite weird to think about, but the math says that. It's just got a really low probability of interacting at any particular long distance. The potential well, and we didn't discuss this directly, so I'll drop in an extra link in about it, also has something called the correspondence principle attached to it. It basically means that as you increase the energy, it starts to look like the classical system, not the quantum system, which is quite cool as well. So what happens when we try to solve these models or these wave functions for an atom? We don't have a box or a ring around an atom, what we have is a nucleus in the middle that'll have a positive charge, and then we'll have an electron whizzing around it in orbit. So we need to work out what is the potential here, what is the potential energy of moving the electron around. And that's fairly straightforward to solve. We've got the charge of the electron and the nucleon. We also know that it must be negative because they're attractive. And then 4 pi for radial reasons. How much it permeates through the vacuum, and then the radius. Basically, the potential energy is only a function of the radius or the distance the electron is from an atom. It is entirely spherically symmetric. You can come at the nucleus from this angle, that angle, that angle, that angle. Doesn't matter, you will feel the same charge, the same pull. The only variable here is radius. We can also work out the potential energy, the kinetic energy as well with the other operator. Let's put a hat on that to say it's an operator. The only change here is that because there are two particles, we need to use reduced mass. We covered reduced mass in physical spectroscopy and also in the lab. Reduced mass pops up whenever we want to simplify a two-particle system. Works really well for a hydrogen atom because we've got one nucleus and one electron. If we start adding a third particle, this function actually breaks down. We can't solve it analytically. The only other thing of note is if you ever see these equations written down, that del operator there is really quite easy to look at if it's in Cartesian coordinates of x, y, and z. But if you start putting it into radial coordinates of a radius and two angles, it actually looks a bit more horrific, even though that's the more convenient system. So I would never ask you to solve that by hand. You might be able to do this in 2 dimensions or even 3 dimensions for a particle in a box, but doing it for an atom is a little bit more challenging. So let's look at what the potential around an atom is. If you simplify it down, it basically is just inverse of the radius. That's not the same as the force, which was an inverse squared law, but it will look a bit like this. It will start really low, come up, and then across and level out. It's an inverse function. It's 1 over. And then negative. That's telling us that as you get closer to the atomic nucleus, the potential energy goes down. You're getting energy back. This makes a lot of sense because we've got a positive charge attracted to a negative charge. They're going to attract each other. You're going to get energy back whenever they get closer to each other. Now, that would naively suggest that the particle or the electron around the atom simply just travels to the nucleus and stays there. And we know that can't be the case. Knowing that that can't be the case is why we have quantum mechanics. Classical mechanics would say that the electron is attracted to the nucleus and then they just collide, they just smash into each other. Doesn't happen. So we have to build a wave function to govern the probable location of the electron based on that potential and how it varies with radius. So when we look at it, and I'm not going to justify these too much, we end up with 4 and 5 maybe quantum numbers that govern the electron. You probably come across this in atomic structure so far. We'll just cover them again. We have n, that's the principal quantum number. Effectively around a hydrogen atom, that's the only number that governs how much energy an electron has. That's why when you look at the spectroscopy, the hydrogen atom and the spectroscopy of the sun, n squareds pop up. It's the only thing we're interested in as far as energy is concerned. Add more electrons in there, it gets a bit more complicated, but we're just going to deal with 1 nucleon and 1 electron for now. Then L, that's the orbital, azimuthal, sometimes orbital angular momentum quantum number. And that, like particle in a ring, tells us how that energy is distributed in angular momentum. So if L is 0, there is no angular momentum. The energy of the electron is only distributed radially. As it increases, the energy of the electron is distributed in an orbital, circular looking fashion, it spins around a bit more. So that increases. And you should know there is also a limit on that. We can't get higher than n minus 1. So where n is equal to 1, the maximum L can be is 0. Where n equals 2, L can be 1 or 0. And so on. So we can distribute that between radial and angular momentum. Then we also have the magnetic quantum number. That tells us how that angular momentum is distributed in space. We'll get onto how that actually looks in the next lecture, because we want to push onto what orbitals look like from a particle model point of view. Then spin. Normally this is neglected for electrons because it's fixed. All electrons have spin equals 1/2. And that's it, that can't change. Spin can change for other types of particles or collections of particles, but for a single electron it's fixed at 1/2. So normally we ignore it when describing an electron because it's not a degree of freedom, it can't be changed. The other 4 can be changed. And then finally, the magnetic spin quantum number, which tells us whether it's pointing up or down. You've been drawing electrons like this for some time, up, down, +1/2, -1/2. We'll get on to spin a little bit more afterwards because we need to get into NMR. So let's look at the principal quantum number. If we try to solve the Schrödinger equation and figure out what the wave function looks like, we get equations that look like this. Now, these do look really complicated, but again, I've color-coded them to break them down into points and different bits. So hopefully you can see what's going on. A here is a normalization constant. You can look up what those are there. Functions of pi, the Bohr radius, and a few other things. Then, although in the first level we don't have it, it's equal to 1, we have this component, which is a polynomial. Now, go back to the harmonic oscillator. Those wave functions also had a polynomial in. They give the orbitals some shape to them. And then finally, each orbital has a very similar looking exponential function. In this case, we don't have the radius, we have rho as a variable. That's just a normalized way of describing the radius. Otherwise, the function would look a lot more complicated. We need more things thrown in there, so we hide it behind one variable. So what do those look like if you plot them? If you copy those down, plot them with a graphical calculator or Wolfram Alpha or something like that, we found that when n is equal to 1, it simply just drops like so. It tends to 0 only at infinity, so that goes off to infinity. And this doesn't actually go up to infinity here. It does cross the y-axis at some point. You just have a limit. And obviously this is radius. You can't get a negative radius, that doesn't really exist. So that's 0. If we pretended we go through the nucleus and out the other side, it then simply just decays on the opposite side like that. So that is what the n equals 1 looks like. If we do n equals 2, well, we've got a bit of shape to it. It's got that 2 minus, and 2 minus rho is a function that looks like that. It's negative. It's 2 negative rho. So if we multiply that exponential by that shape, we get, it must hit through 0 there, and then it comes back up, and again continues on to infinity. And if we do 3, we get kind of the same thing. It comes down, crosses again, and down. Here we have 2 points where it crosses the x-axis, or 2 nodes. So n minus 1 nodes at any point. Once we've got more than one node, that allows us to distribute them around the atom instead in an angular fashion. So let's go back to the next quantum number, L, the angular momentum quantum number. How does that work? So this tells us how much angular momentum an electron has in total. How much of that energy isn't with it bouncing back and forward in a straight line out from the radius, but going around almost. So when L equals 0, it's not circling around like this. We couldn't really interpret the electron as orbiting in a conventional sense. It's actually oscillating back and forward through the middle of the nucleus. So it might go back and forward. There's no real circular motion to it, which is a bit odd to think about, but you know, it's a valid orbit. That's how it works. As we increase L, that motion becomes a bit more angular, a bit more circular. And so we use the particle on a ring to help briefly justify this. This works in 2 dimensions. You can kind of extend it into 3, but that's then easier to approach in a different way. So let's just recap what that looks like. If L equals 0, our wave function is completely flat at L equals 0 on particle on a ring. It could be has an equal chance of being found anywhere in any angular direction. When we increase to 1, it's not the same as the particle in a 1D box. It goes up, down, and up. Remember, it has to do that because periodic boundary conditions means it must be in the same value and the same direction. We also get one that's offset by 90 degrees, a sine or a cosine wave, a positive or minus value. And then if we increase it further, we get a wave that looks like that. Again, another one, this time actually offset by 45 degrees, but you can see the same sort of pattern. So we have one that may be a positive quantum number, one that might be a negative quantum number, circling clockwise, anti-clockwise. So that's fine if you look at it in 1 dimension going back and forward like this, but what if you plot it going around a circle? So here, our L equals 0, or angular quantum number is 0. The value of the wave function is the same all the way around. And we can visualize this by just plotting a color for whether it's positive or negative as we go around the ring. So we can see 0 degrees here, 180 degrees here. It's the same. It's going to be blue all the way around. We increase that quantum number. Suddenly we've got a positive side and a negative side. It's going to be 0 at 180 degrees, 360 and 0. Well, 360 and 0 is the same. 180 is the opposite side to it. So we actually have a node going through the middle of that. Now this makes spotting nodes on a particle in a ring model actually a little bit more difficult when you're in that form, because you might think, oh, it crosses the x-axis here, here, and here, therefore it's 2, maybe 3. It's only 1. These are the same node when it's plotted like this. And of course, if we have another function that's offset by 90 degrees, well, we can rotate this 90 degrees as well. We have a node going through here. Maybe 90 degrees there, 270. So between 90 and 270 degrees, there's that node going through. Those are starting to look like p orbitals. And yet, if you take one of those exponential functions we looked at earlier, multiplied it by this as a radial distribution, you get a p orbital exactly out. You could plot that in a 2D calculator. You take the 3D version, you can plot it into a 3D graph. So these are very related models. If we increase it up again, well, yeah, same argument one more time. We've got nodes across here, but that actually translates into 2 nodes. And these all look like d orbitals. So this is only the 2-dimensional case. If you remember your atomic structure, there's actually 5 d orbitals that are all degenerate. This might suggest there's more or fewer. We will get onto why it's fewer on the next lecture, because we're going to approach it from a quantum number perspective. For now, we're just justifying the shape of these by relating it back to how this model works on a ring. Right, so let's recap. The model systems give us things like quantization. That's reflected in reality. They also give us degeneracy. more than one quantum state that has the same energy, again reflected in reality. It's really useful to be able to connect these simplified models to something like a real atom, even if you can't do the maths behind a real atom, which I wouldn't expect you to do. It's a little trickier. And we can also justify the shape of the atomic orbitals as well by looking at these models. The 2D and 3D box, for instance, can sort of help justify how p orbitals are shaped. They can't really justify how d orbitals are shaped, unfortunately, but there is a nice analogy connecting the two there. So all of those properties are seen in real atomic orbitals. So that's it. This is just a quick recap of how models relate to atomic orbitals. In the lecture after this, we're going to consider them purely from quantum numbers and angular momentum, because once we get angular momentum, we can move on to spin and then finally move on to magnetic resonance.